So I'm James. I'm back to give a second talk on a different topic. So for this talk, I'll tell you about how we can actually use Twitter to help us to build visual language models, right, for medical AI, for pathology. It's actually a good segue from Violet's talk just prior, right? And this joint work with my good friend Elon. But of course, actually the real people that led this work are Zhi and Federico, who are two terrific postdocs working with me at Stanford. Right. So what we want to do here is to basically leverage the data that we can actually, medical information knowledge that are shared on Twitter. Right. I'll tell you about how we can collect that information and curate that. And the visual language model we're talking about here will basically be a model like GPT-type models, right, but have additional understandings of computer vision, right, of understanding these pathology images. Right, so I'll also give you a bit of a tutorial of how we actually build these kinds of models. Okay, and similar to the first talk, you feel free to interrupt me if you have questions. Right, so the motivation here is that if we look at standard clinical workflows, right, oftentimes people spend a lot of time looking at these histopathology images, which are an example of these images shown here, right? And these images are very routinely collected to help pathologists to understand and to diagnose diseases by looking at cellular and tissue architectures. Right? A lot of time they actually spend manually looking at those images either under the microscope or on their computer monitor. And because these images, histopathology images, are very prevalent and because they're clinically really important for making diagnosis, right, there has been a tremendous amount of interest in developing computational and AI methods to help to analyze these kind of images. Right? So this whole field of computational pathology. The field has actually been, I think, making a lot of exciting progress, but there's also, I think, quite significant data challenges. Right? So one thing that makes this computational pathology quite difficult is just the heterogeneity and the diversity of different diseases. Right? There are often many thousands and tens of thousands of different diseases and diagnoses that one might want to make from these histopathology images. Many of these diseases are quite not so common, but the typical public data sets that we have are much more limited, right? For example, if you look at TCGA for cancer, there's only on the orders of a few thousands of these annotated images, right? Which only covers the more common diseases and cancer types. And in addition, many of the public data sets are also very limited in their annotations. Right, so most of these data will just tell you that, is this patient, do they have cancer or not cancer, right? But doesn't really, these kind of binary or categorical labels, but does not actually tell you more detailed information that are contained in these sort of rich textual descriptions. So the existing public data sets are quite limited, but in parallel, right, there's actually a very active community on Twitter of people sharing this knowledge, right? So for example, there are many pathologists, if they see an image or case that maybe they're curious about or they want to get some help to analyze, they often actually post the images on Twitter, right, and ask their colleagues to comment and to help them to discuss these images. Right? So you have the images, and then you have the entire Twitter thread of pathologists chiming in from all around the world to discuss what's going on in each of these cases, right? And so our idea here is then to see, okay, can we actually harness all of these medical knowledge that are shared publicly on Twitter, right, to help us then to build a language model that can understand this pathology language, but also understand the pathology images, right? Because it becomes like a dialogue agent then to help pathologists to diagnose new patients or to retrieve information. So that's the motivation, right? So what I want to do today is to first tell you a bit about how we actually curate this data set from Twitter. So we call this data set OpenPath. It's all publicly available. And in the second part, I will tell you about how we can then leverage this OpenPath data set to build one of the first visual language foundation AI models to help us to understand pathology images and text. Okay, so first, so how do we actually go about actually systematically harnessing all of these knowledge that's shared on Twitter? So we're actually very fortunate in that so US and Canada Association of Pathologists, right? So this sort of these high-level organizations, they actually very early on proposed several set of specific hashtags to recommend the pathologists to use when they're discussing these new cases. Right? So here are some examples of these hashtags. Right? So you can have different disciplines of pathology looking at breast or colon. Right? Each of those disciplines will have their own specific hashtags. And basically, then we can look at all these recommended hashtags and use them as a way to initially to curate all of the tweets. And then we have additional filterings, a lot of stringent filterings to remove the noise in the Twitter data. Right? So we can have classifiers that can look at each tweet and say, is this likely to actually be medically relevant? Right? And then we filter out the tweets that are not medically relevant. We also filter out tweets where the images are low quality, where if it's not written in English, we'll filter those out. And this was basically collected all the way from 2006 until end of last year. So after we do this curation and filtering, we end up with over 200,000 of these high-quality image and text pairs, right, from these Twitter threads. Right. So I think this is actually one of the largest such data set, visual language data set to date, right, in pathology. And so the examples we see here are basically just for each of the hashtags. There are 32 different hashtags for each of the hashtags. How many tweets we can actually have curated, or high-quality tweets we can curate for each of these hashtags. Right. So for example, for dermatology, for DermPath, right, so we can get over 23,000 of these tweets. Each tweet would have one or more high-quality images, along with the corresponding text that describes this image. Right? And in addition to the original tweet itself, we also look at replies that have the most number of likes, right, which gives us sort of additional information. So often these replies, sometimes the initial tweet will contain like a question around what is in this image, and then the top replies will then contain discussions or answers that describes what are the relevant medical information that's in these images. Right, so we also get the replies. So typically, these tweets would have on the orders on a median around 30 to 40 words, right, which actually contains quite a lot of information about these images. Right, so beyond just the binary classification labels. Cool. Any questions about how we curate this data sets? OK. So this is the open path data set. And we made all of this publicly available. So now once we have this data set, right, so again, the data set now basically contains these hundreds of thousands of image and text pairs. We can actually then train visual language model to help us to understand these kind of image and text pairs. Right, so the visual language model have these basically two components. Right, there's like the text encoder and an image encoder. Right, so both of these encoders are different types of transformers. Right, but the main idea here is that the text encoder is going to look at basically the text part of the tweet, right, and encode that into some sort of vector embeddings or representations. And then the image encoder, which is like a visual transformer, is going to look at the images in the tweets, right, these pathology images, and then encode that in terms of a vector embedding. So here are some of the examples of the kinds of text we can get from the tweets itself, right? So there's our shown on top, and then the images are the kinds of images we find that are embedded in the tweets, right? So how we then train these, so the key part here when we build these visual language models is basically you want to align the visual understandings with the text understandings. Right? So the text part would be like a standard kinds of GPT or ChatGPT type models, right? But those standard models actually do not have the GPT-4 actually does not have the image understanding part, right? So at least not yet. So the key part here is that we basically want to align the text understanding with the image understanding, right? And we do this basically by different types of contrastive learning. So here's like an illustration of how the standard contrastive learning works. Right? So we start with a bunch of these different texts, right, from the tweets. Right? So each of the text here, right, each of these sentences here then will be fed into the text encoder, and it will correspond to the different vectors, right? So T1, T2, T3 are, think of those as basically being the vector embeddings corresponds to the text from the first, second, and third tweets. And similarly, the images would also be fed into the image encoder to produce I1, I2, right? So the I's here will correspond to the image embeddings. Because we know which image corresponds to which text, right? So we know that the diagonal element, if I look at the dot product, right, between that embedding of the images and the corresponding embedding of the text, right, so those should have high similarities, right, if I have a good alignment between the visual and the language parts. Whereas the off-diagonal elements should have lower similarities, right? Because those corresponds to taking a tweet and a different image from a different tweet, right? So we want to have the embeddings to push those farther apart, right? So the way this is trained is basically essentially by optimizing this objective, right? So that the diagonal element, right, of this paired language and images have high cosine similarities or high dot product, and the off-diagonal elements would have low dot product. Right? So this is basically how the standard approach for how we actually train visual language models to align the language understanding with the vision understanding. Right? So there are lots of additional tricks that we can do to make this work more efficiently. Right? So instead of, for example, just taking random pairs, right, of off-diagonal elements, which corresponds to sampling like negative examples randomly, we can actually have more adaptive or clever ways of sampling these negatives to force the model to basically learn more efficiently. This corresponds to basically selecting hard negatives. But the high-level idea would be the same as we have here. Yeah.
So is that image encoder maybe working on the whole image or maybe on the region of maybe interest? Because I think in the text, potentially that only describes some part or maybe some object on that images, not the whole images.
Yeah, so it's a good question. So in the tweets themselves, often people would post, for example, a patch of the original host slide. Sometimes people actually put like a much larger image, like for the bigger slide, but oftentimes they put different patches, right? So basically the image encoder here would be a visual transformer, but we actually do a lot of different data augmentations to basically crop it and to change the magnification. So the image encoder is actually looking at this image at different resolutions. Okay, so this is the algorithm we call PLIP, right? So it's very much sort of inspired by this algorithm. It's called CLIP. It came from OpenAI, which is basically not medical specific, but it's actually trained on billions of image and text pairs from sort of natural images, which is sort of one of the first foundation model to do visual language understanding. Right, so the PLIP one is basically the pathology specific model that we basically fine tune on top of CLIP. Okay. So this is actually how we build these models. So for the remaining part, I want to tell you about how does the community typically evaluate these kind of visual language models, right? And this also illustrates the kind of applications that might be interesting on the clinical side. So there are basically like 4 main types of evaluations. Each of this corresponds to a different type of applications, right? So I'll tell you a bit about how we do these sort of zero-shot evaluations of these visual language models, which essentially corresponds to giving it new images, ask it to make new diagnosis that has not been trained on before. Right? And also tell you a bit more about how we actually leverage the representation learning capabilities of these models. And finally, we'll talk about text-to-image retrievals and image-to-image retrievals. Okay, so starting with the zero-shot classification, right? So recall that the way we train this model is just purely based on the image and text pairs, right? We didn't actually train the model to do any specific pathology classifications or diagnosis, right? And the idea here is that even though we did not train the model to make those specific diagnoses, the model actually has learned enough capabilities about the images and the text to be able to make a new diagnosis by itself, right? If we can do this, this will demonstrate very high sort of what we call zero-shot performance. Zero-shot here means that we didn't actually give it any training data for that specific task. So the way that we actually use this PLIP model to make zero-shot classification is as follows. It's quite intuitive. Right, so let's say if the user actually has a new image, right, it's different from the Twitter training data. So we can get to the image encodings, right, for that new image by feeding it through this image encoder, right? So it gives us the embedding I, right? And then we can, behind the scenes, generate all sorts of different text corresponds to different diagnoses, right? That might be relevant for this image. I can say, okay, this is an HAE image of a tumor, of adipose tissue, of lymphocytes, right? So each of those will correspond to like a potential candidate diagnosis or a description of the image that we also generate behind the scene, right? And then for each of those candidate descriptions, right, we can feed it then through the text encoder to generate one of these embeddings T, right? And then simply pick the text embedding, the text description that has the highest similarity equals dot product with the image encoder, right, with the image embedding. So this would be like a very simple way to directly use the text and image encoders to do these zero-shot classification. Right. So the benefit of doing this is that because the Twitter data is actually very heterogeneous, right, there are actually lots of rare diseases, diseases that are discussed on Twitter. Like if it's people typically will talk about shared images that are harder for them to diagnose, or less common images, right? So then this kind of zero-shot performance can help us to basically diagnose sort of new or less common diseases. Great. So then we evaluated this on sort of 4 sets of downstream tasks, right? The details here are not so important, but each of these tasks are sort of existing public databases that are different, right? That are not overlapping with the Twitter training data, right? And each of these data sets will correspond to have their own set of different annotations, right? Different data sets have different annotations. Some data sets will have annotations about whether these histology images corresponds to tumor or normal tissues, right? Other data sets would have more like different, which tissues are involved, right? Is it from stroma or lymphocytes, right, in these images? But in each of these cases, we can just use the strategy that we mentioned on the last slide, right, and ask the algorithm to automatically do this zero-shot classification. Yeah.
In your previous slide, are you basically just guessing text and then checking to see which one matches? And you can sample the whole space of possible text in a reasonable?
Yeah. So basically, we have.
Like that n is a big number, right? It's not like.
Yeah. So there's like a list of maybe hundreds or thousands of potential diagnoses that people might be interested in. So those are all pre-computed, right? The text embeddings are all pre-computed, and given an image, a new image, we just see, okay, so which of these pre-computed text embeddings actually have the highest similarity to it? Okay. Yeah, so that would be a very simple way to use this model. Yeah. And the point here is just to demonstrate even like these very simple approaches already actually works quite well, right? So basically, this is like the kind of the zero-shot F1 scores, right? If you actually just do this very simple algorithm on top of PLIP, right, across these 4 different data sets, right? So you can get sort of relatively good F1 scores from above 0.5 to 0.8, right? And the baseline here is sort of the CLIP model, which is, we said, is sort of the previous, this very large vision language model from OpenAI. It's been trained on billions of text-image pairs. So that includes some medical image and text, right, but also includes a lot of other things. And here is just demonstrate. So these 2 models, PLIP, our PLIP model and there's no OpenAI CLIP model, they actually have very similar architectures. Right? So this is actually mostly to demonstrate that by doing this additional training on this Twitter data, we can actually really significantly improve the model's zero-shot performance in recognizing these pathology-specific diagnoses. Okay. And we did a lot of additional evaluations here. So you can also say, okay, so the previous result is looking at aggregate across all the different tissues, right? So here you can also break it down by different, different organs, different tissue types, right? So this is just basically to show that even if you look at the more granular tissues, right, so the models, like this PLIP model's classification performance is actually pretty consistently higher than if we use the OpenAI models that's been trained on the more natural images. And this, I think, also demonstrates the benefit of leveraging the Twitter data because it's very heterogeneous and diverse, right? It comes from all these different tissues and organs. This actually helps the model to generalize better to these different, to different subtypes. Okay. So the second application, right, is on basically showing that the split model is also very good for learning representations, right? Now these zero shots are a nice demonstration, but it's often not how we really want to use these models, right? So what you really want to do is to basically take the embeddings from these models and maybe train a classifier, right, for each of your specific tasks or application domains. And this is what we do here, right? So we will basically take this image encoder from PLIP, right, just to learn the representations. And then we can actually train simple machine learning models or even simple linear classifiers on top of this representations, right, to predict new diagnosis of interest. And this just demonstrates that if you actually do this on top of the PLIPS representation, right, you often can get much better performance compared to the zero-shot performance we saw before, which is not surprising. But the more interesting part is that the performance by taking the PLIPS representation as a starting point, right, is actually much better than if we start with other representations that people have developed before. Right? So for example, MoodiePath is actually like a big multitask learning problem specifically designed for pathology. Right? It's actually meant to do good representation learning for these kind of pathology images. And if you take those embeddings as a starting point and then train the same classifier on top of that, you can get pretty good, but often worse predictions compared to if you take the PLIPS representation as the starting point for training these models. Right. The other way we can actually test the benefit of these image representation learning is by looking at data efficiency. Right. So here it's basically saying that for each of these specific downstream classification tasks, how much data do we actually then use to train that downstream classifier? Right. So here on the left here will be if you use this really small amount of training data, and then as you go towards the right, you're using a larger and larger amount of training data. Right. So the curve in blue corresponds to the F1 performance, basically the accuracy of the PLIP model, and then the red one corresponds to if we actually use a different model like the visual transformer. Right. And here this basically really demonstrates that, especially when we have smaller amount of training data, right? So doing these kind of fine tuning on top of the PLIP representation is actually much better than if we actually train the model on top of other representations like these visual transformers. Which is also sort of a way to demonstrate the representational benefits of these contrast learning trained on this large Twitter data. Okay, so the third set of applications and tasks is for text-to-image retrieval. Right, so here the usage scenario would be like, imagine if you're a user, right, you may just want to type in like a natural language description of the kinds of things you're interested in. Right, like almost like a semantic search, right? Maybe you want to look for like normal colon, mucosa in colorectal tissues, right? So that would be your input query. Then we can then also use the PLIP text encoder to embed that input query, right? And then just simply use this to retrieve images from Twitter and also from hospitals, right? From any database, right? That have the highest similarity compared to your text query embeddings. Right? So this can be done very quickly. And we can then evaluate this. Right? So one way we evaluated this is that the original model was actually trained on all the Twitter data from until end of last year, right? So end of 2022. Then for the earlier part of 2023, there's additional tweets, right, that we can curate from the pathology Twitter. So each of those tweets then will correspond to like a new data point, right? They have the images and the text pairs. Then what we can do is to basically put this new tweet text, right, into the search engine and see how often would we actually pull up the exact image that was embedded in that tweet. Right, so that would be a very direct way to validate this model. Right, we can also ask it to query textbooks and other databases or PubMed articles. And the way that we evaluate this sort of standard approach is basically look at the precision. Right? Precision at 10 basically means that if I return the top 10 search results, right, how often would the exact tweet image, right, the ground truth actually be contained in one of these top 10 results. Right? So among all the possible thousands or tens of thousands of possibilities. Right? And this is also to demonstrate that with this representation learning, right, with PLIP, the text-to-image retrieval is actually many folds better than if we actually use other models. Right? Maybe 4 to 5 times better than if we actually use other text-to-image retrieval models. And the last application is to basically do the same kind of thing for image-to-image retrieval. Right? So here the usage setting is, imagine if you're a pathologist and you have some images, right, and you don't quite know what's going on in this image, and then you can put that into the search engine, and then to pull up additional images from or additional tweets that are maybe seem to be discussing similar cases. Right? And you can then use that information to maybe help you as second opinions or to help you to generate some additional hypotheses. And here, basically, the idea is then we're given new query image, right? So we can look at the image embedding of that and then basically compare that against the image embeddings of our database from all the tweets and medical records and to pull up the most relevant ones, right? And here the evaluation then would be, okay, so if we look at across these different data sets, right, how often would we retrieve images that come from the same tissue type, or from the same organ, or have the similar kind of staining styles, right, or other biomarkers, right? So we need to go into all of the details here, but just to show that across all of these different evaluation tasks, right, so the image-to-image retrieval performance of PLIF, which is the blue curve here, is often relatively good, right? So it's sort of the state of the art for doing this image-to-image retrieval now for pathology. Okay. So we actually built like a demo, sort of a search engine. It's hosted on Hugging Face. You can try this out now, right? So this is a live search engine where you can either do text to image, right? You can write in your text and then search for the images. Or if you have your own pathology images, you can do the image-to-image search, right? And here's an example. You can put this in this image, right? And then our search engine then will basically pull up all of the relevant tweets, right? That discusses cases that are the most relevant or similar to your query image, right? And the way where we're going next with this is to basically build like the fully integrated chat PLIF, which is like essentially the multimodal chatbot, right? That can look at this image and automatically provides these text descriptions and diagnosis, right, from each of this pathology image. And at the same time, it can also pull up all of the relevant discussions that people had, both on social network and also on your private EHR database. Right? So the query can be done not just over the public Twitter data set, but it can also be done on your private EHR digitized pathology data sets. Right? So this is what we call ChatFlip, which we're essentially deploying initially at Stanford and then hopefully more broadly. So just to wrap up here, so I guess the two main messages here at first is that I think there's actually certainly there's a lot of noise on Twitter, but there's also a lot of actual valuable scientific and medical information that are shared on Twitter, right? So it's a really useful public resource if we figure out a good way to systematically curate and harness those information that are shared on social media, right? So OpenPath is an example of how we can actually do this for pathology, right? And doing this, we actually created, I think, one of the largest publicly available data sets, right, of high quality pathology image and text pairs. And then to demonstrate why this is a useful data set, right, so we then developed this visual language model that can be used for these different applications. Yeah, so all of this is publicly available, and I want to acknowledge again, so Zhi and Federico, who the postdoc who led this work, is also collaboration with Tom Montine, who's the chair of pathology department at Stanford. And yeah, so we're excited about, I think this is sort of just the tip of the iceberg of what we can do with these visual language models for specific domains like medicine, right? And oftentimes, like getting the right data is basically the biggest barrier for training these models. Right? A lot of the data sets are sitting at proprietary hospitals, right? But I think this is where having these, be able to curate large public data sets, right, from social media, I think it could be a good way to go around these bottlenecks. All right, so I'll stop here and happy to take more questions.